All right, if you want to title this like predicting the wavelength of light for transmissions in the hydrogen atom. Transitions. What am I saying? Transmissions for transitions. Predicting the wavelengths of light for transitions in the hydrogen atom. Here is our equation, our first of multiple equations. The energy of a photon that gets emitted when one of these transitions occurs is equal to the negative RH, that's a Rydberg constant. That's a capital R sub capital H, Rydberg constant. Talk about what that is in a second. Times 1 over n final squared minus 1 over n initial squared. Copy that down. And we'll talk about what these three things mean. Energy equals negative RH times the quantity 1 over n final squared minus 1 over n initial squared. First, let's start with the Rydberg constant. The Rydberg constant is 2.18 times 10 to the negative 18th joules. And final squared, this is the orbital where the electron stops. And initial squared, this is the orbital where the electron starts. So for example, we'll do one here in a second, but let's say I wanted to calculate the energy of an electron going from the third orbital to the second orbital. Well, if the electron's here going here, the final would be 2. That's where it stopped. And the initial would be 3. That's where it started. So we would do negative 2.18 times 10 to the negative 18th times the quantity 1 over 2 squared minus 1 over 3 squared. That's it. And that would get us the energy. And once we have the energy, we can get the frequency using Einstein's equation. And once we have the frequency, we can get wavelength. So it's a 3-step process, okay? And it starts with this equation. This equation allows you to get the energy of a photon emitted when an electron transitions within the hydrogen atom. So energy equals negative RH times 1 over n final squared minus 1 over n initial squared. Let's do one. Here we go. Super excited. I forget what I got here. Let's do a 4-to-1 transition, folks. Let's do a 4-to-1 transition. So I'm going to walk you through this guy together. All right, so we want to get the wavelength of light emitted for an n equals 4 to n equals 1 transition. Let's do it. So energy equals negative RH times 1 over n final squared minus 1 over n initial squared, where RH is 2.18 times 10 to the negative 18th joules. So energy equals negative 2.18 times 10 to the negative 18th joules times 1 over, we're going from 4 to 1. So the final 1 squared minus the initial 4 squared. Go ahead, see if you can't pop that in your calculator correctly. Now, I usually kind of take a cheat. Like I would do, I would do like 1 minus the quantity 1 divided by 16. And then I would multiply whatever, as long as you get the right answer. See if you can't get that energy. Go ahead. All right. I got negative 2.04 times 10 to the negative 18th joules. And here's the first time where we need to talk. So first of all, did we get that? Give me a thumbs up if you got that. That means you're using your calculator right. You know what's, you got that going. Okay, we got a couple thumbs up. That's good. Ah, there you go. That's all. Most of you. Very good. Let's talk about what this negative means. This is the first point of confusion. This negative does not mean mathematical negative. When you're doing these equations, if you get an answer that's negative, it means energy is released. You can't have negative energy. That's not possible, right? Energy is energy, right? It can't be negative. Okay. So when you get a negative answer here, it means the energy is released, and this should not be surprising. We are going from a higher energy excited state, n equals 4, all the way down to the ground state, n equals 1. Energy is being released. That's what that negative sign is telling us, folks. So once you understand that, that makes this next step a little easier to understand. What are we going to do? When we have the energy, we can now use that Einstein's equation we were talking about earlier, E equals hf, and we can use that energy in Planck's constant to get a frequency. But when you do this, that energy has to go in as positive. You need to, if you got a negative energy here, you need to drop the negative sign before you go on to the next step. Leave it here. That tells us energy is coming out. It's being released. It's not being absorbed. If I was going from 1 to 4, I would have to absorb this much energy. We'd get a positive answer. So if I switch those two, we'd get a positive 2.04. Okay? But we need to drop that negative before we take it to the next step and do some math. So I like to do algebra up front. I'm solving for frequency. So I'm going to divide both sides by h. The frequency is equal to the energy divided by Planck's constant. So let's plug this in. We're going to plug this in as a positive value. The frequency equals positive 2.04 times 10 to the negative 18th joules divided by Planck's constant. That's 6.626 times 10 to the negative 34th joules times seconds. Take a second to catch up. So what happens here? Obviously, joules cancel out. We're left with per seconds. We're going to get an answer in hertz or cycles per second. Go ahead and bop that in your calculator. Hopefully using that E button. Hopefully you bought into the E button by now. You should get 3.08 times 10 to the 15th hertz. Take a second. If you didn't, pop it back in. Try again. We're still not done. We want a wavelength, but we're almost done. We're getting there, folks. Okay, so hopefully you got that. Now what? Now, last step, lambda equals c over f. Speed of light, 3.00 times 10 to the 8 meters per second. Frequency, 3.08 times 10 to the 15th cycles per second. Seconds cancels out. We're going to be left with a wavelength in meters. And we get 9.7. I think we still got 3 sig figs. 9.74 times 10 to the negative 8th meters. And I would like to know, hey, can we see this? Can we see this line, a 4-to-1 transition? Well, this is why you need to memorize the visible spectrum, being 400 nanometers to 750 nanometers. We're going to convert this to nanometers and see if it falls between 400 and 750. If it does, it's visible. We should be able to see this photon of light. If it doesn't, it's not visible. It's going to be infrared or ultraviolet. So let's do this. 1 meter, 10 to the 9th nanometers. So 9.74 E negative 8 times E9, and we get 97.4 nanometers. So this is not visible. That wavelength is too short. Okay, too short. This is ultraviolet. It's an ultraviolet emission line. We can detect it, okay, with a detector that picks up UV light, but you'll never be able to see that light, with your eyes in a spectroscope. Woo, man, we gonna practice a bunch in the lab tomorrow night. You're gonna do a bunch of these calculations. So, but I do want to do another one here. I want to do a visible transition, but I want to make sure we're all on the same page. Quick recap: what did we do? We started with this equation. This equation allows us to get the energy of a photon for an electron that's transitioning between energy levels in a hydrogen atom. Then once we got that energy, even if it's negative, we make it positive. Once we got that energy, we use Einstein's equation from the photoelectric effect to turn that energy into a frequency. Take the energy divided by Planck's constant, gets you a frequency, right? And then once you have a frequency, we can use this good old equation we used at the beginning of class, wavelength equals C over F, lambda equals C over F, and we can turn that into a wavelength, and then you can see if it falls in that 400 nanometer, 750 nanometer range. So I want to try another one here before we take a break. Let's see, blah, blah, blah. Let's go and let's do a visible one. Do we do red or aquamarine or violet? Which color should we do? Let's do aquamarine. I want to do a 4-to-2 transition this time, folks. I want to do a 4-to-2. So watch this. It's pretty awesome having a board. I want to do a 4-to-2 transition. So I'm going to give you a couple minutes. I would like you to calculate the wavelength of light associated when an electron in a hydrogen atom jumps from the 4th orbital to the 2nd orbital. Go ahead, give that a shot. You got this. Let's try this thing. Here we go. It's ending in 2. So 1 over n final squared. That's 1 over 2 squared. And it started initially in 4. So maybe you want to rewrite that as 1 over 4 minus 1 over 16. However, I don't care, man, as long as you get it right. Or it's a moment of truth right here. I got negative 4.09 times 10 to the negative 19th joules as the energy of that photon that's going to be emitted, that energy that's going to be released when the electron goes from 4 to 2. So now we're going to use Einstein's photoelectric effect equation. Again, just light work tonight, just a little quantum mechanics. Who doesn't do that on a Monday night, right? I mean, come on. It's like refreshing, right? Now you guys are doing great. Hang in there. Okay, you need to drop this negative because that's not a mathematical negative. That negative means energy is being released. So we're going to drop it. It's just going to mess up the math, right? That's not what that negative means. So 4.09 times 10 to the negative 19th joules over Planck's constant. 6.626 times 10 to the negative 34th joules times seconds. Joules are gone. Left with answers of seconds in the denominator, which is a hertz. And we're going to get 6.17 times 10 to the 14th cycles per second, or hertz. And now we can solve for a wavelength. Wavelength is c divided by frequency. So 3.00 times 10 to the 8 meters per second divided by 6.17 times 10 to the 14th cycles per second. Seconds gone, left with an answer in meters. That's 4.86 times 10 to the negative 7th meters. 1 meter, 10 to the 9th nanometers. So that's 486 nanometers, which falls in the visible spectrum and should absolutely be visible. In fact, if we go back to that slide we were just looking at, 486 nanometers. Isn't that crazy? That is crazy. Okay, yeah, like you guys are doing quantum mechanics tonight. It's exciting. You're talking about, I mean, this is real deal. This is legit quantum mechanics that you guys are doing. Yeah.